So it's my distinguished honor to kick off the 2022-23 MateriAlZ seminar series. My name is Bruno Azeredo. I'm a professor in manufacturing engineering at Arizona State. On behalf of the organizing committee, I would like to welcome you all to the MateriAlZ seminar series, which is held in partnership between material science enthusiasts from University of Arizona and Arizona State to promote our field and beyond Arizona as well. You can find us on our website, social media. We're very active. Is this our third or fourth year, Ankit?
I think this is our third year. Yeah.
All right, we're headed into our third year. We're very excited. Not to put any pressure on our guest today, but the first semester of every cycle is a distinguished scholar. So Judson, you have that honor today. I want to thank all of my co-organizers as well. So Ankit, Christina, Krishna, and Marat are here today. And so without further ado, let me introduce our speaker today, Judson Ryckman from Clemson University. I actually know Judson quite a while. I first met him when he was just a piece of paper and I was reading his papers. I initially didn't thought he was going to be a nice guy, but then I ran into him into conferences and got to know him better. He completed his PhD in electrical engineering at Vanderbilt University, working with Professor Sharon Weiss. He then moved on to work at Intel as a research scientist, as a photonic design engineer, and got some great, experience commercializing the release of their first silicon photonic products back in the days. And since 2016, he's been an assistant professor in the field of nanophotonics, silicon photonics. I'm very excited. He's received many awards over the years, particularly 2 Young Investigator Awards from the Air Force and from NSF. So we're very excited to have you here, Judson. Great pleasure to host you. So floor is yours.
All right. Yeah, thank you, Bruno, for the invitation and everyone for organizing this. It looks like you have a very vibrant community, so I'm very happy to be a part of this seminar to present some of our work. And it's also a unique opportunity to kind of zoom out a little bit on some of the things I do that sometimes seem disconnected. But I'm going to try and paint with some broader strokes today and connect things together. I'm in the electrical engineering department at Clemson, really focusing in photonics. But the fact this is a materials-oriented community made me think a bit more about the platforms we use. And the common thread in everything that I do really is silicon, which is kind of a surprising optical material. So that's really the theme of my talk. Is I'm attempting to weave together these both silicon photonics and porous silicon photonics together, and hopefully show you some interesting applications along the way. So with that, let me attempt to click OK. So a brief outline of my talk. I'll do a quick bio about myself, and then talk a bit about silicon photonics, which as a term has its own kind of interpretation. But it's a very broad field, just using silicon for optical applications. I am going to steer toward the subwavelength domain, as that affords a lot of exciting opportunities to engineer light matter interactions. But I also want to talk about the different processing techniques available when we try to structure silicon. So whether it's top down or bottom up, we'll touch on all of these. I'll show you a few examples and highlights from our own group. And then hopefully toward the end, we'll take a deeper dive into one specific application, and that is hardware security. And of course, open it up for Q&A. So just quickly about myself, I grew up 2 blocks away from the Wright brothers' home in Dayton, Ohio. Did my grad school at Vandy. And as Bruno said, I spent a few years at Intel working in the silicon photonics group. And now I've kind of gone coast to coast Although when you think of South Carolina, you think maybe of Myrtle Beach. We're about as far away from Myrtle Beach as you can possibly be and still be in South Carolina. So we're about a 4 or 5 hour drive from the coast. You will see Clemson tiger paw print featured throughout my presentation here. I've learned that, Clemson folks are very proud of this logo, so I use it quite a bit. And it has to be at exactly a 2 p.m. angle, otherwise someone will give you an odd look. But so that being said, let's back up and talk about silicon, okay? So silicon is kind of a, I wouldn't say paradoxical, but a surprisingly good optical material. So on paper, 30 years ago, you would have said silicon for optics, what are you going to do? Photo detection or solar cells, right? It's indirect band gap, so light emission is not really a good option, but certainly light absorption. So, certainly in the visible range, it's a great photo detecting material, low cost, and all of this. So this was up till about 1985. This is the dominant consideration for silicon as an optical material. But there are some other perks. So it has a very high refractive index. And it also has infrared transparency, which if you're doing telecommunications, well, you're using wavelengths in the infrared. So this is very attractive. And folks were starting to consider, single mode waveguides and stuff in the mid 80s, but there was no clear application because fiber was working great. And there was not too much else exciting about silicon as an optical material until along came Richard Soref in 86, 87, and he discovered that not only does it have a high refractive index, but it can be tuned via this plasma dispersion effect, which is essentially if you can control the density of charge carriers, either electrons or holes in silicon, you can now change the refractive index. And that immediately opened the door to all kinds of optical switches and modulator technologies, and really brought the silicon as an optical platform closer to electronics, and really kicked off the field of silicon photonics as we know it today. So if we look at this term silicon photonics and you look at sum of citations per year, right? So kind of the obligatory chart in a seminar of a particular field, you see a very strong growth over time, really kicked off from the late 80s. So there's a lot of development. And of course, some of this growth is because it's really tapped into different application areas and has gained more and more research and commercial interest over time. So, at the turn of the century, so the early 2000s, there was a lot of development, higher speed modulators, interconnection, and really the driving force was overcoming the interconnect bandwidth limit of copper connections. And also the light source dilemma, really the inefficient indirect band gap problem of silicon was really overcome thanks a lot to the Bowers group and integration of 3-5 bonding onto silicon. This process has matured in wafer scale foundries where you take existing CMOS processes and now pattern silicon, typically silicon on insulator waveguides or wafers to make waveguides, and process these at scale. So these are 8-inch wafers. And of course, one of the products I worked on at Intel is called PSM4, and it was 100G, really oriented for data center communication. But of course, despite this being the driving force, there's been a lot of other exciting application areas. So sensing is certainly one. You see a lot of LiDAR interest recently, and quantum information, and much, much more. And so if you look at this, we're using what in the mid 80s seemed like a very boring optical material, but it's become very exciting. And there's lots that you can do if you structure silicon and engineer it in the right way. So if we back up and say, okay, we want to structure silicon, how are we going to do that, and what types of geometries or devices are we going to achieve? Well, we have a few different tools, right? So we can go from the top down, use more conventional CMOS processing, etching, maybe subtractive manufacturing techniques, or we can use some more self-organizing bottom-up type approaches. So I'm going to try to touch on both of these, because this, I think, is where the intersection of silicon photonics and porous silicon photonics really comes through. But in the end, we're just structuring silicon in different ways. So first, let's touch on the top-down processing techniques. So some of these are my group's work. On the left, this serpentine image, this one is not our group, but it's one of my favorite kind of exemplary images of a silicon photonic structure, because we can bend a waveguide in this nice, beautiful serpentine, because, and you see how tight the bend radius is. You could never do this in an optical fiber, really, because we have the high refractive index. The mode size becomes very small. So it goes with the refractive index squared. It's inversely proportional to that. So having that high refractive index, infrared transparency helps a lot. So this is more of a wavelength scale type of device, and it's really diffraction limited waveguide. Now these 4 examples on the right, this is research out of my group, where we're starting to play, you know, at smaller and smaller scales. So some stuff, what I kind of broadly say the subwavelength scale. So one example, this is theoretical work from a couple years ago. We showed that you could engineer the cross-section of a silicon waveguide to achieve an ultra-low mode area. So you can really squeeze light and locally enhance the electric field to be much stronger than you would otherwise expect based on the diffraction limit. And this is really thanks to just pure electromagnetic theory, Maxwell's equations, and the fact that there are interfacial boundary conditions that have to be obeyed. So that introduces a variety of effects, subdiffraction effects, polarization dependencies that you can really engineer. And so we've spent a year or two actually trying to fabricate some of these devices, and we have some more fresh off the press results that we're hoping to publish soon with these ultra low mode area waveguides. We've also taken silicon, and instead of just structuring it with a periodic pattern like a Bragg structure or a grating, we've started to engineer different types of periodicities or Moiré effects, which I'll touch on more in a second. And we've also taken other structures outside of waveguide platforms with something like a Me resonant nanodisk, and started to introduce subwavelength features into the disk to control the electromagnetic near field and provide even greater electric field enhancement.
Judson, sorry to interrupt. Could you just say what range of wavelengths, photon wavelengths, you're working in here?
Yeah, thank you. So almost all of these are infrared wavelengths, so 1310, 1550. This is maybe the exception. This one is resonant around 1064. But yeah, thank you for bringing that up. Yeah, so mostly infrared. And if I touch on this one a little bit more, so we've seen this theme recently of Moiré effects in 2D atomic materials. And this was part of our inspiration really to explore this. There's a variety of unconventional properties like superconductivity, localization, Moiré excitons, a lot of exciting emergent properties that can be tuned by just simply twisting a few different atomic layers together. And so we took a similar idea and said, let's apply this to a one-dimensional structure. So we're taking a two-dimensional Moiré effect and doing a one-dimensional Moiré effect. And now we can do this in an optical platform, and we have some advantages over the material sense, because there's such a precision required and a delicacy to the processing of these layers that in an optical platform with a top-down processing technique, it's very straightforward. So we can on the fly design a new structure with a different, period 1, period 2, and do a wide variety of studies on the different Moiré effects. So there's some kind of fundamental studies we can do, but also some application-based studies. So we explore this. What I'm showing here is a typical way you might measure these structures. If this is a finite, we call it a silicon nanowire, but it's really an optical waveguide that has this sidewall modulation. And we can couple light in and out using these grating couplers. So it's very convenient, and we can have lots of devices on a given wafer. So that provides a lot of freedom from the top-down sense. So save this one. I'm going to revisit this later on, and we're going to actually use this in our application for the security-based application. So we'll come back to this. And if there's more questions on this or this particular paper, I have a few backup slides, but there's some other items I do want to get to. So that's maybe a preview of some of the top-down stuff, and we'll revisit the security application from the top-down perspective. But I want to talk about bottom-up processing of silicon and spend some time here. So what do I mean by bottom-up? Right. Well, this hopefully gives the impression. We're going to use chemistry. We're going to use self-organization phenomena. And so there's a wide variety of ways to structure silicon at the nanoscale using self-organizing phenomena. So one of the most popular, one that we use, is the electrochemical anodization of silicon in the presence of an HF electrolyte. So this was accidentally discovered, I think, in the 1950s, while attempting to electropolish silicon. Every now and then there were these discolorations on the surface, and it was later determined that it was a porous material. It would even change its color if it was wet. And it really is this nice, delicate, porous network, and there's a lot of different morphologies. The pore size can be tuned. This process proceeds preferentially along a certain crystal orientation. So this particular example is a 100 silicon single crystal wafer that is then anodized. The process consumes holes. So if you use an N-type wafer, you need to illuminate. If you use a P-type wafer, you do not. And you're left with some of these byproducts, but a very nice, a porous and high surface area material. This has lots of applications beyond photonics. There's a lot of biomedical applications, drug delivery applications, but we're especially interested in the photonic applications. And this was really kicked off in the early 90s. So this, the work of Lee Canham, he discovered photoluminescence in porous silicon. I think it's been said this APL paper is perhaps the most highly cited APL paper of all time. Has over 12,000 citations, I believe. And so it's discovered that and later determined or attributed to the nanoscale quantum confinement effects at the surface, as well as other surface effects that contribute to the quantum emission and photoluminescence. So there was a ton of interest in the 90s in this material, which later on kind of tapered off when the stability and low efficiency were kind of shown. But a lot of other applications persisted, and certainly in sensing. So this is a little bit of our work that I'm going to expand on in just a minute. But we use porous silicon because it is a very simple and cheap platform where we can get tunable optical properties and a high surface area for capturing small molecules. So I'll expand on this one in just a minute. Of course, you can structure silicon into quantum dots or into nanoparticles to use or to achieve PL or I think my light just turned off. We're in an energy efficient building, so if I don't move, my light will turn off on me. So hopefully you can you guys still see me okay?
Yes.
Yeah, you're
Okay.
fine.
Okay. So yeah, lots of different bottom up or self-organizing effects. And again, all of these are really just silicon, but structured in different ways. So this is an example of resonant nanoparticles with different structural colors. So let me talk a little bit about our sensing work with porous silicon. So we use it as sort of our sensing substrate, if you will. And we came up with this technique called hyperchromatic structural color, where instead of shining ambient light or white light on a sample, we're going to illuminate it with laser light, and specifically at least two different wavelengths of light. And in this case, I'll show the RGB case, so red, green, and blue laser wavelengths. We have a porous silicon film, which serves both as a host to capture small molecules, but also as an optical film that has tunable properties. And it has a reflectance spectrum that will shift or perturb in response to these molecules. So physically what happens here, and it is important to note that porous silicon, because the pore diameter, let's say 30 nanometers, is much, much smaller than the wavelength of, say, visible light, say 500 nanometers, it acts as an effective medium. So we have a refractive index that's between that of silicon and air. And as you add more molecules inside, the refractive index goes up and the optical spectrum will change. So the idea here is to make a sensor that can be read by a camera or even by, say, the naked eye. So how do we do this? Well, one, porous silicon is widely used in the biosensing community because it has one of the highest sensitivities. That is the spectral shift that you can obtain, the delta lambda, per unit of, say, small molecules either bound to the surface in some equivalent add layer thickness, like a 1 nanometer monolayer, or some mass surface density, say picograms per millimeter squared of molecules, will provide a very high wavelength shift. And that's really because the effective refractive index, the delta N of the material itself, increases quite a bit thanks to the high surface area and tunable pore size. So this is much better than even a plasmonic or an evanescent, say, silicon photonic resonator type platform. But this is only one piece of the puzzle. We need not only to maximize the shift, but in our case, we're interested in maximizing, say, the color change. So to maximize the color change, which can be measured in different ways, it can be measured as a Euclidean distance delta E in a particular color space. We use a perceptually uniform version of delta E, so I won't get into all the nitty-gritty details, but we want a large perceptible color difference. Meaning, for example, you want to go from something like green to magenta, and that will provide a large delta E versus, say, light green to bright green. So we need both of these. And to obtain the second piece, we found that using multiple laser wavelengths really allows the maximum possible delta E per delta lambda. So that is, if this sensor shifts its spectrum in response to the analytes, the color change is maximized. And so what I'm showing here is actual experimental data where we demonstrate this effect. In this case, this is not small molecules. This is just the infiltration and surface absorption of water vapor into the pores. So you see, if we have the sample in air, we have the black spectrum, a standard Fabry-Perot interference pattern based on the R1 and the R2 of the top and bottom interface. And as you infiltrate, say, water and begin to fill the pores, the refractive index goes up and the wavelength begins to shift. In this case, as we infiltrate water vapor, you see a very strong color response. And I'm going to show you an actual video of this sample. So that you can see a sample like this is about a quarter, the size of a quarter. You can hold it in your hand. In this case, we're shining RGB light on the sample. There's some nuances to this that I won't really get into, but if there's questions, I'm happy to talk about. We're looking actually not at the sample directly, but you can kind of see here, we shine the laser light here and let it project onto a screen. So we're actually viewing the screen itself, which will provide an angularly invariant color, much like if you're sitting in a movie theater and just looking at the screen. So here's a sample here that you can see starts off as kind of this magenta red, fractions of it are a little bit yellow on the edge. But this is a porous silicon thin film interferometer. It's about 1 micron thick, and it has pore diameters around 30 nanometers. So let's take a look at what happens in response to water vapor. So you see pretty immediately as the vapor begins to condense inside the pores, there's a strong color change. And it really is, this trajectory in white here is actually measured from this video, which is taken with an iPhone camera. This also illustrates one of the nice advantages of colorimetric sensing. It's not just a yes or no type of response, but it's a spatially mapped response as well. And so we actually see the evaporation of the water vapor out of the pores. And this is effectively a very nice structural color effect, where we've combined both the porous silicon and a special illumination strategy. So when we combine those two things, that really allows us to get a maximum color shift per unit analyte. And we've begun doing more sensing type experiments with this. I'll show just one example where we take a porous silicon chip here, and we're going to functionalize the surface, and we'll be able to see it by the naked eye, despite the fact that these molecules are, in this case, it's about a 0.8 nanometer, roughly a monolayer, versus about 1.5 nanometer to 2 nanometer molecule. So we're going to do this Venn diagram type experiment. So we'll silinize the surface to give a nice amine termination, and then we'll come in with this sulfo NHS to bind to the available amine termination. So here's our aminosilane. We can see it's changed the color of the sample. It's increased the refractive index, and as we've measured also the optical properties of the sample, we're relatively confident that we haven't done a really poor multi-layer, but it's a pretty well behaved monolayer. Come in with our sulfo offset, and we see that specific binding where we only put down the sulfo NHS biotin where there's an amine terminated surface. You do see a little bit of non-specific interaction. There's a light color change here, and we can do more sophisticated image processing on this type of sample to really measure what's going on. But you can see we've transduced the presence of a thin monolayer of molecules, which you might otherwise need, say, an ellipsometer to do. And now you can see it by the naked eye or a smartphone camera. So that's one area that we work in quite a bit. And that's our application of the bottom-up form of silicon. So just porous silicon structured in the right way. Okay, so I've talked a bit about top-down processing, bottom-up processing. There is something that, I haven't coined a great term for this, and maybe someone out there can coin a better term. I'll just call it hybrid processing. That is, you take components of both. For the really nanoscaled stuff, or for the intricate stuff, you can use the self-organizing effects, but also combine some form of top-down processing to enhance the functionality or performance. So you can get sort of best of both worlds capabilities. And so we're going to look at this with silicon as an example. So one example, this is work not from my group, but this is Jason Valentine's group out of Vanderbilt, where they've taken polystyrene beads, which can self-organize, into a close packed arrangement on a surface. So that's kind of your self-organization piece. But then you can do top-down processing and put it into the clean room, do reactive ion etching. And so now you have a nice arrangement of these Me resonators on the surface with a tunable size, and they give a very strong coloration, tunable spectral properties on the surface. So in this case, this is self-organization of the polystyrene and then top down of the reactive ion etch. Another example, this is not our work, but this is Paul Braun's group out of UIUC, where they take first top-down processing of silicon to make these kind of, I don't know if we call these microscale kind of rectangles or pillars, but then come in and do the self-organizing porous silicon etch. So it's put in an electrochemical cell in the presence of HF, apply a current, and as you change the current density as a function of time, you can actually program in the pore porosity and therefore program in the refractive index. So they've achieved these programmable gradient refractive index micro pillars, if you will, and they have some interesting optical properties and lensing effects and birefringence properties as well. So this is a really nice example of combining top-down and bottom-up processes. Again, both of these end up with just silicon, but structured in different ways. So this is work out of my group. We've taken a similar idea to what Paul Braun has done here. And we first pattern silicon. So we go ahead and do conventional photolithography and etching just to make this, this rib structure. But then we go in and we anodize the sample in our etch cell, and we do it in 2 or 3 layers. So first we etch a low porosity layer, and the low porosity layer, because it has a higher fraction of silicon, a lower fraction of air, it has a higher refractive index. But then we continue the etching and increase the current density, and that allows us to increase the porosity. So now suddenly we can make a high refractive index, low refractive index structure. We make optical waveguides, in this case, a rib waveguide, which is now porous. So that means analytes can infiltrate inside of the waveguide rather than being limited to evanescent interaction that you would have in a conventional platform. So this is one example. And as we characterize, say, the sensitivity of this type of structure, if you look at its response to, say, small molecules, you'll see that the porous structure has about 2 orders of magnitude larger response than the evanescent or non-porous waveguide. So we really boost the sensitivity, and we think this could allow us to drive the limit of detection down much lower than more conventional platforms. So another example of hybrid processing, this is some work that we've done recently where we've shown not only can you change the refractive index electrochemically by changing the porosity, right? You can change the refractive index mechanically by compression. So if we take a high porosity porous silicon film, let's say it's 71% porous, maybe the film looks like this. Again, I mentioned those pores are much smaller than the wavelength. So we don't have very significant scattering. We have a relatively well-behaved effective medium. And you see that in the Fabry-Perot interference measurement, which matches the model pretty nicely. The refractive index is pretty low. It's 1.4. We could make it even lower if desired. But when we compress the film mechanically, we reduce the fraction of air, and therefore the porosity goes down. The refractive index has to go up. So we now have a mechanical means of tuning refractive index on the surface of a chip. You see here this example, the relatively large area uniformity, several millimeters squared, kind of handheld chip type of measurement here. And this is a pretty broad effect. Oh, my lights came back on. So I'm going to revisit this one in just a second. I do want to touch on a related one. And so this is actually work out of Bruno. Bruno, I think you did this when you were a grad student, actually. So this is maybe the paper he was alluding to before. But this is another nice example of, kind of a hybrid top-down, bottom-up. So this is some of his electrochemical imprinting work, which he's continued to do very nice things with. I think he's demonstrating some micro optical concentrators here. And again, using self-organizing electrochemical etching combined with some top-down patterning. So all these examples are just silicon, but structured in different ways. So I'll pause for a minute to expand on this one, because we've started to branch out. This has a lot of different potential implications, if you will, that if we could pattern this process, it would be possible to achieve, for example, an effective medium metasurface where you manipulate the wavefront of an incident waveform or plane wave by manipulating the phase. And traditionally, this is done by some structural change or size of a pillar or meta atom. But in our case, we could do it in a very smooth or digital fashion by simply changing locally the refractive index. So it is possible with our process to pattern the refractive index potentially with a high spatial resolution and high contrast. And so we have some recent work where we explore this capability. This is currently work that's been submitted. So we demonstrate digital and gradient refractive index patterning. So we'll compress our structure, but now we're using a more sophisticated stamp. And so depending on the geometry and the imprint pressure, we can change the refractive index on the surface. So as we compress the film more and more, really the porosity goes down and the refractive index goes up. There's also been some maybe unexpected findings here that the refractive index will not actually return to the refractive index of bulk silicon because there's always a native oxide that's present. So that does reduce the refractive index. So we can get up to about 2.6 because there's a sizable surface area of SiO2. But even then, our refractive index dynamic range is quite nice. It's over 1 RIU. And so we've also demonstrated some gradient index structures. So we'll planarize these films, and we've demonstrated some micro lenses based on porous silicon to do some wavefront shaping. So this is sort of our first demo, if you will, of an experimental effective medium metasurface. But we can also make in-plane devices, so we can imprint digital structures, and we can also fashion waveguides, and might use those for, say, sensing applications or low-cost, very low-cost integrated photonics. So we don't need an expensive SOI substrate. We take a very cheap silicon wafer, and with the right processing, we can make all types of optical structures from it. And if you have the right stamp design, then in principle, this really opens up the freedom to manipulate wavefronts, and you become limited really by the stamp fabrication process. So this is one thing we're working to refine more and more to demonstrate more advanced types of structures. Okay, so that's hybrid processing. We talked about top-down, bottom-up, hybrid. Again, all keeping within the silicon theme. And check me on time. I think we're doing okay. But in the last, say, 10 minutes or so, I want to do a deeper dive on one specific application that we've gotten involved in, and that is hardware security. So in this case, we'll borrow from our top-down structure of silicon, slightly more conventional silicon photonics. Some of the Moire stuff is going to be embedded inside these photonic circuits, and we'll see what kind of role they can play for hardware security. So first, let me motivate this a little bit. I think we've certainly seen in the news, right, since the pandemic, the role of the semiconductor supply chain, right? It's become this big term recently, mostly the bottlenecks in terms of processing time, chip deliveries. But it's also true that the semiconductor supply chain, aside from being complex, it's disaggregated and it's global. So you send chips all over the world for processing, for packaging, for testing, for retesting, repackaging, etc. And so your intellectual property is mailed overseas and is potentially vulnerable to malicious actors, right? So whatever they're trying to do, insert some backdoor, counterfeit your chip, steal the chip and replace it with another one, etc. There's a lot of potential vulnerabilities. And so one question is, how do you assure that the hardware is authentic, it's not modified, it hasn't been cloned or counterfeited in some way? And the other thing to keep in mind is that electronic technologies are increasingly vulnerable. So we can't just store a digital password on the chip and say, if we get the chip back and it has the same digital password, everything is fine, because it'd be very easy to steal or modify a digital signature. So instead, we want to use a physical, hardware level property of the chip itself to prevent this. And so that is kind of the idea here, or the motivation. If you're a manufacturer and you have many different chips that go out into the world, into the supply chain, when you get them back at end of line or end of packaging, how do you verify that it is the chip that you originally sent out? So let's use a physical hardware level and non-digital property of the chip. So some kind of physical key that you need to extract from the chip. It should be physically unclonable, so no one could possibly replicate this property, which also means it should be very complex and information dense. So it can't just be a few simple signatures, but it should have a lot of information content to it. Of course, we need it to be CMOS compatible and scalable. Otherwise, it's not going to help out with the semiconductor supply chain. And moreover, it needs to be practical, meaning that if we measure the signature over time or over environmental variations, it needs to be reliable, it needs to be robust. So optics has begun to play a role in this field, and this actually started in the early 2000s with the idea of a physical unclonable function. And so this can be as simple as taking a rough optical surface and shining a laser beam off of that surface and looking at, say, the speckle pattern. So you'll get this very information dense, information rich pattern that should be unique to that particular rough surface. And you can extract information from it. You can then digitize it to make it more measurable, in that you could compare it before and after processing. And there's a few important important traits here, is that any two chips obviously should have a very different signature. So this is measured as an interchip distance, and something that's called the Hamming distance. So if you digitize to ones and zeros, you can compare two different keys, for example, see how similar they are. If they're fully uncorrelated, the Hamming distance will be 0.5. And if they're exactly the same, the Hamming distance will be 0. Of course, you allow for some bit errors. So there's ideally authentic devices have a small Hamming distance, and non-authentic have a Hamming distance near 0.5. So the speckle pattern is one way to do this, but of course it's not very integrated, and it's also in its own way a very delicate and sensitive type of measurement. So imagine trying to reproduce this exact speckle pattern 100 times or 1,000 times. It's going to be very environmentally sensitive and sensitive to probing conditions. So there's a variety of optical platforms you could imagine using: random optical media, different types of speckle patterns, even types of on-chip devices, which have been studied maybe more in the context of, say, different applications like spectrometers, where you use the disorder to generate a random speckle pattern, and that speckle pattern can give you a spectral resolution that's very high. So these devices, although they weren't discussed as such at the time, actually are physical unclonable functions. is they cannot be exactly reproduced. Also, we see more recently intentionally designed physical unclonable functions based on multimode fiber, the speckle patterns you get out of those, and now more integrated work out of Amy Foster's group at Johns Hopkins, compact chaotic resonators. Now, many of these platforms suffer from a really strong sensitivity, not only to the structure of the device, but of the environment. So you see this example here. Despite being unclonable, it's also will decorrelate with itself if the temperature is shifted by 0.16 degrees Kelvin. So this is also a problem that needs to be addressed. So if we get back to our work, what have we done? Well, we've taken these, conventional optical puffs, and we've said, okay, they have certain environmental and probing sensitivities, and a lot of that comes from the fact there's many modes. Those modes might interact with a thermo-optic material in different ways. That can be measured as a confinement factor. And the probing will also excite different weight fractions of those modes. So we said, let's back up and just use integration to our advantage. So using our on-chip grading couplers, single mode waveguides, we can filter out a lot of the probing variation. So if the optical fiber is twisted a little bit or misaligned, well, that issue is going to be filtered out because of our grading couplers and waveguides. And now the optical design is also done a little bit carefully. It's not too multi-mode. It's really mostly in these single mode waveguides where we can achieve a pretty uniform confinement factor, meaning all the modes in our structure will have a similar or almost the exact same thermo-optic sensitivity, and that will allow us to mitigate the temperature effects. So as we look at this device, this is a photonic circuit we made. So it's all silicon, but it's on insulator, of course. So these waveguides are about 220 nanometers in thickness, about 500 nanometers in width, and sitting on an oxide cladding, and they're also overcoated with an oxide. What we do is actually, if you're familiar with an interferometer, right, split light into two different paths and look at the phase delay. So one simple way to do that is a Michelson interferometer. So here's a loop mirror that just reflects the light back, and another one to reflect back. But instead of a conventional Michelson interferometer, which would certainly be clonable, we insert these quasi-crystals, which are basically small corrugations on the waveguide using this Moiré pattern, and also the fact the spiral has a varying radius of curvature. So this quasi-crystal breaks the translational symmetry, and it essentially introduces a very high sensitivity to nanoscale perturbations. And you can even visualize some of these, this is manufactured imperfectly. There's sidewall roughness, there's nanoscale errors in the width, and we're going to harvest those errors such that any two devices we fabricate, despite having the exact same design, will give completely different output behaviors, and that makes each one unclonable. So how we do this? Well, without getting too detailed here, we have this effective index profile, which you can think of sort of like, the electron particle in a box, kind of standard quantum mechanics, but instead here think of optics. We have some potential landscape of high and low refractive index that could potentially confine or transport block modes through it. But in the fabrication, there's a disorder that occurs. And this disorder is not repeatable device to device, and it introduces lots of interesting effects. Some states become localized, others just shift their optical response. And so the output of this particular interferometer becomes very disordered. There's actually signatures of Anderson localization with some of these resonances, but the phase spectrum and the amplitude spectrum become unclonable from device to device. And We compared this, we took our, what we call the quasi-crystal interferometer, the QCI. We compared it to a more standard modification of a Michelson that is just put an extra resonator here to introduce an extra etalon type of effect. And even though this one can have device-to-device variations, if you manufacture enough of them, some of them will be identical to one another. And in fact, device 2 and device 3 were very, very similar. So you can see how clonable this would be. You could not manufacture millions of devices and expect them to all be unique, for example. Whereas here, we think that is indeed the case. We'll get a unique signature across potentially millions of devices. So the key to this is we're using a device that has no translational symmetry, and it's sensitive to distributed fabrication errors at the nanoscale, whereas this type of device really compiles all the fabrication errors into an ensemble effect, and it's not very complex or information dense. So the temperature piece, maybe I'll talk about this in a second, but what we see here, if we take, for example, the first, we call this a puff, or the physical unclonable function. If we take the first puff and we look at its temperature sensitivity, we'll see this complex spectrum really just purely shifts thermo-optically, because the index of silicon goes up with temperature. And so thanks to the design being single mode in the transverse dimension, we get a pretty nice spectral shift that's retains the same signature. So if we want to authenticate many different devices, well, we just need to measure their spectrum and store that in the database. So we'll measure the spectrum, and really the grating coupled measurements are, this is a highly automated process. This is done in silicon processing, wafer scale. It's highly automated. So we think this is a potentially scalable technique to be measured at package after packaging. But so let's say we take our spectrum and we need to digitize it. We have a few tricks here where maybe we remove most significant bit, but we do some type of analysis. In this case, we'll do a cross correlation between two keys and determine if it's authentic or not. So if we look at this, here's just a snapshot of many different devices. We've now manufactured or compared a recent batch of, say, 56 puffs, which allows us to, say, compare this puff to all other 55 puffs and verify that it's unique, and do that again and again and again. We can compare 3,000 devices, inter-device comparisons, to really prove that it's unclonable. So here's an example of the digital signature that we might extract from one of these waveguides. And actually, this is all 56 waveguides. We're zooming in on a small section of what I believe is a 7,000 bit long digital key. And if we look at this key, it does shift with temperature. So if we change the temperature, the spectrum will shift, but that really just shifts where the ones and zeros are along the key. So there's a few bit flips here and there, but it's mostly just a shift of the entire key itself, which is nice. It means that we can use a cross correlation to authenticate any two keys. So if we measure puff number 1, it should authenticate with itself, and we see it's highly correlated to itself, despite the fact that the temperature has changed, but it does not correlate with any other device. And so we see this puff 2 correlates with itself, but not any other. And here's an example. I think this is puff 14, correlates only with itself and has no correlation with any other device. So this really shows that it is unclonable. And we also mitigate the temperature drift effect. So if we analyze the results of all 56 devices, we see nice correlation with themselves, meaning we have genuine authentication with a 0% error rate. And we also had a 0 false authentication. So no two devices accidentally had the same signature. They were all unique. And now that we have more statistical data, we have an actual distribution of the authentic devices here on the left, meaning, the authentic devices here on the right, meaning high correlation, and the non-authentic devices here on the left. We can compare the tails of the distributions, and somewhere there is a non-zero intersection of the tails, and that's how we estimate the probability of cloning. And it's extremely, extremely small because we're at a very large number of sigma away on both of these distributions. So it really is unclonable, although there's a finite non-zero clonability, but in practice, this does not matter. And then maybe I'll close on some more forward-looking opportunities. So we've begun to make more active versions of this. So you can imagine use silicon photonics and optoelectronic integration to actively change the properties. So we can have a given puff signature that now, instead of just having one fingerprint, it could reconfigure, and we could potentially achieve thousands or maybe millions of different fingerprints within a given footprint. And so we're trying to increase the information density of this platform because it could be used for more than just authenticating a device, say in the supply chain, but data storage or encryption, key exchange and communication, and lots of future opportunities in authentication and security. So I think that brings me to the conclusion. So hopefully I'm not too far off on the time. So I really tried to cover a lot, but we're really just structuring silicon and doing it in different ways. So my group, we tend to work at the nanoscale. We use a mix of top-down and bottom-up processing, explore all three of these, and that's where we obtain really maximum versatility for structuring these devices is at the subwavelength scale. So with that, I want to thank all my students, many of whom have graduated from the Ryckman group and contributed to these works, as well as our collaborators. A special thanks to Lucas Krastowski and his team for helping with some of the silicon photonics endeavors, and also NSF and AFOSR for their support. And thank you all for having me at this seminar. Happy to answer any questions.
All right. Thank you, Judson. One of the very sad things about Zoom is not being able to effectively, enthusiastically convey clapping. But please feel very warm and a warm salutation from all of us. All right, so we're going to move to the question and answer. So the way we typically do, folks, is to let us know that you have a question, and then we're going to work to unmute you and let you ask the question live. So it looks like we've got the first one coming up. So SK Day, would you please unmute yourself and ask your question? Oh, it looks like he doesn't have a mic, so I'm going to ask the question. On the long-term reliability and performance of such porous structures, is there any fatigue or aging upon use? That's the first question. And then the second question is, what is the effect of a fixed charge, mobile oxide charge, oxide trap charge, and or, oh, this is a little difficult. DT in the vicinity of the silicon non-stoichiometric silicon oxide interface. Judson, tell us what you understood of the question, and please.
Yeah, so I think the first part, in terms of porous silicon, and I don't know if I'll bring up a visual here or not, but it is sensitive, and so what's nice is that we rely on the surface oxidation to really stabilize the structure. So once we oxidize the surface or achieve a native oxide, it's stable in an air ambient environment. It can still be unstable in an aqueous environment. So depending on what's in that environment, it will degrade or dissolve. It's biodegradable. So there are ways to improve that if needed for long-term use. we certainly have chips sitting around in the lab that have been around for years that are just, hanging out and doing fine. I think in terms of the second question, maybe I can read the chat, but to some extent, so optically, we tend to be immune to the charge effects, but maybe the question is breaking the centrosymmetry of the material, like at a surface, which is certainly, I think, possible. You could get interesting surface effects or stress effects, which could be present. There are stress optical effects in porous silicon. We don't use that much. And we imagine there could be in some of our more nanostructured waveguides as well. But yeah.
Great. Let's move to Peter. Peter.
Hey, Judson, thanks for the nice talk. So going back, my question about the wavelength, and you were saying that you were working on the infrared, but I think for the sensing, you were working with visible, is that right? So with silicon, even with polysilicon, do you not just, when you go to visible light, do you not just get attenuation of the photonic modes because of absorption above the band gap? How does that work?
I guess, we really benefit from the fact that it's porous. So our silicon fraction goes way down, and then it's oxidized. So that further reduces.
I see. So it's really silica. It's really mostly silicon oxide with the wide band gap, and then the effective medium theory. When you have the adsorbates going down, it changes the refractive index essentially of the silicon oxide component, I guess. Is that right? Is that, and the silicon's not so important?
That's right. So
I see.
We have somewhere, we'll model, say, this Fabry-Perot spectrum, and we'll include the N and the K.
Right.
But the K won't really matter too much until we get to several microns.
I see.
Tens of microns. Yeah.
And do you find that the effective medium, are you just assuming the refractive index is the volume weighted average of the two components? Does that work quite well?
So there's a slight modification. We use the Ryckman effective medium theory. So there's a different equation that works well for interconnected networks. If you have sparse ones, there's a Maxwell Garnett, but we pretty much.
Okay, right. Okay, thank you very much. Thank you. Thanks.
All right, we have one more question from Mukesh. Mukesh, would you like to unmute yourself, please?
Thank you, Dr. Judson, for a nice talk. And my question is, how can I determine the number of pores and pore volume in a silicon porous film?
Okay, yeah. So I guess there's a few different, measurement techniques. So you can do a standard SEM image, and then there's some distribution analysis you can do to see what is the average pore size. You can, let's see what else, cross-sectional. There's also some more advanced techniques with, gas absorption analysis to get the average pore surface area, get the specific surface area of the entire system. We also use gravimetry, where you actually measure the mass of the chip before and after peroxifying it to see how much silicon you remove. So there's a few different techniques like that. I'll say in our case, the pores are disordered, so there's not a single tubular diameter. It's, there's some disorder. So there's a mean pore diameter and some type of distribution around that.
Thank you.
Bruno, I have
Go ahead.
Yeah, I think Peter kind of has the answer that he gave kind of makes this answer almost redundant, the question, but you looked at the effect of mechanics or a mechanical force or on changing the porosity or changing the refractive index. Could you apply a field to change the refractive index, but now with the silicon oxide as being the down one, maybe not?
So that's a really good question. So if you want to apply a DC field, so silicon is not, at least classically, it doesn't have, say, the Pockels effect, so that electric field sensitivity, but there have been some demonstrations of like a DC Kerr effect in, special types of silicon that might be doped or has stress. So that could be possible. In our case, we haven't really studied that. But certainly the plasma dispersion effect would be there. If you change the charge carrier density, you'll have some index change.
And very quickly, you only looked at physically adsorbed rates, right? I mean, and if you have chemically adsorbed, where there's charge transfer or something, that could also in principle shift.
Yeah. So we do tend to look, say, if we're doing, binding of molecules to the surface, we're using the fact that this Aptes molecule or this biomolecule has a refractive index that's larger than the medium it's displacing. So we really use that effect. So we haven't done too much with charge, although there are charge corrosion effects that occur that could amplify in some cases, but mostly just refractive index based.
Okay, thanks, Judson. Thanks a lot from the UFA behalf too. You have a class? Oh. Okay. It turns out that we have to log off Bruno and Judson because apparently there's another class scheduled for this.
Sure.
All right. We'll work out the timing a little bit better next time. Thank you, Krishna.
Bye all.
Thank you, Krishna.
Bye.
We have one more question here lined up, Judson, from Sandia. Would you please mute yourself and ask your question? Hi, Sandia. Are you there? We cannot hear you. Let's see. Oh, okay. Well, I have a question, Judson, before we break out. Some people have to leave, but so when you were doing the puffs, I like the word, by the way, puffs, very catchy. So did you have any Moiré patterns there to induce these signatures, or you still just rely on whatever these noises are coming from? I guess, it's all tied to some defects on the manufacturing processes. Were there any intentional structures you added, or were they just randomly formed?
Yeah. No, that's a really good question. And it's probably, I kind of don't explain that maybe that well, but it is indeed so there's a very intentional design so the fact that, say, we choose this period to be 316, and we choose this period to be 317. The 316, if it was just this, it would produce a Bragg diffraction peak or a Bragg mirror around 1550. So that would put band edges around 1550. And on the band edge, there's a very high sensitivity because light slows down. So it becomes more sensitive to perturbation. But when you mix it with another, you can imagine two competing Bragg mirrors that begin to overlap with one another. So you not only have the band edge effects that occur. So actually, when we measure the spectrum, you see all of the disorder really shows up kind of in this window. So if we measured it at, say, 1700 or at 1300, it would look more clonable, because we're far away from the Bragg window, if you will. We're away from the band edges. So that is kind of an important nuance that I maybe kind of, we might have missed.
And so if I'm going to try to physically clone your device, right? So let's say, at some cost, everything might be clonable one day if you put enough effort into it. So in this case, the secret sauce would be the 316 versus the 317. That will be, if I were able to get that information and make an exact same thing,
Right.
would that give me the ability to clone it? What's the
No.
key?
So we copy the design exact 56 times, the exact same GDS design, and all 56 come out different. Right.
Okay, so why does that, what's the underlying reason for that?
So it's,
So let's
it's
say,
just-
okay, so you have the
Yeah.
geometry there, you made it, the 56 different devices,
Mhm.
316, 317. Why, and what do you associate? Why are they all unique?
Right. So if you look at the interferometer itself, the phase is acquired based on, how much silicon is there, and even small little changes in where the silicon is. So nanoscale width variations will change the phase of light as it goes through this structure. And, maybe it's not super obvious here, but there are these resonances as well, where light will just kind of sit and dwell. And those resonances appear because of the disorder. So they might not have actually been there in the first place, but because of the roughness, you suddenly get a localization event or an Anderson localization where the phase changes very rapidly with wavelength. So it's the unique distributed errors in the waveguide width, which are sort of unavoidable. So this is not intentional. This just happens basically.
And that's so all naturally occurring variations during micromachining of the waveguide.
Right.
Beautiful. No, I think that's, really kind of seeing that connection to how that was created. It's really kind of important to me, and I really, really impressed with that. That's awesome. Do we have any other questions? In that case, I think we're gonna call it off, Judson. I want on behalf of the committee, thank you for an amazing talk. I hope you get to visit us soon in person sometime, and when you're around, let us know and show you around here at ASU. Okay.
Yeah, thanks a lot for having me, and really glad to get to do this, and hope to stay in touch, and thanks again.
All right.
All right.
Bye, everybody.
you.
Bye, Ankit. Bye, Christina.
Bye. Bye.
Bye.